Good day, everyone. Today we will be addressing one of the questions that we posed last time, namely, when can we say that an estimator is good or not? Our approach will be to analyze in detail a very simple example. This example captures the fundamental ideas that we want to illustrate, and at the same time is simple enough so we don't get distracted by unnecessary details. Let us consider the problem of estimating a constant given noisy observations of it. This is a problem that emerges when one wishes to estimate the direct current level in a signal, for instance in electrical engineering, but it also arises in many other applications. Let us assume that the constant is deterministic and that the noise samples are random, zero mean, with variance sigma square and uncorrelated along n, which means that any pair of noise samples are uncorrelated. The entire discussion will build upon basic probability theory. You may check your knowledge by answering these questions. If you find the smallest difficulty in doing so, I recommend that you watch the review video on probability theory earlier in this series. Using probability theory, and it is easy to see that these assumptions here imply that the observations are also uncorrelated along n. And introducing the additional assumption that the noise is Gaussian distributed, then one can conclude that xn needs to be also Gaussian distributed with this mean and this variance, and the entire the vector collecting all the observations is multivariate Gaussian distributed with this mean vector and this covariance matrix. Here this symbol represents the vector with all ones, and capital I denotes the identity matrix. The problem is given the data, estimate A. So A here plays the role of theta in the notation of the previous lecture. Let us see how this data looks like by means of this very simple MATLAB code snippet. Here, please remember that the number that multiplies rand n should be the standard deviation. It's a common mistake to write here the variance instead. If we execute this line multiple times, then we will obtain multiple realizations of this data vector x, and 4 of them are represented here. We see that the samples take values around this mean value of 70, and the deviation is greater the greater the standard deviation that we specify here. As an exercise, you may try to generate realizations of this model over here and plot them as well. In order to develop a notion of what constitutes a good estimator, we will consider 4 possible estimators and experiment with them a little bit to see how they behave. In particular, we will be considering the sample mean, which in principle is what intuition asks us to do, but we will also be considering this estimator, which just returns the value of the first sample, this estimator which returns the value of the last sample multiplied by 3, and this one over here which always returns the same number. Please remember that all of them qualified as estimators because they return a real number, and the parameter that we want to estimate is precisely a real number. The first approach that may come to our minds to compare these estimators is to generate a data vector, evaluate these estimators to obtain the corresponding estimates, and then we see how far these estimates lie from the value that the true value of the parameter we want to estimate. So this is carried out by this code. This is the same as we had before, and this line over here evaluates these functions to compute these estimates. So one possible output that we may get is this one over here, where this is the data vector and this is the vector with the estimates. The first entry is the estimate produced by the first estimator, and so on. So in this particular case, we see that the estimator that returns the closest estimate to the true value is the second one. This goes against our intuition that this one was the best estimator, right? So, but does this mean that this estimator is the best out of these four? And the answer is, of course, no. This occurred for this specific realization over here, but if we run the code again, then this comparison may be different, and perhaps the one that performs best is the first one rather than the second one, right? So what we observe here is that evaluating the performance of an estimator based on a single realization doesn't really make sense. We need to conduct a statistical analysis where we consider multiple realizations of the data. To this end, we need to decide on how we are going to quantify how well an estimator performs on a set of realizations, or potentially on all realizations. So the metric that we had in mind is not satisfactory because it can only accommodate one single realization. We need to go for metrics that assess performance on average. So suppose that we generate a collection of realizations of the data vector, and we evaluate our estimator for each of those data vectors. Then we will obtain a collection of estimates. One, in principle, would expect that a good estimator returns estimates that lie on average close to the true value of the parameter. And this is why we typically use, one of the performance metrics that we typically use is the so-called bias, which is the difference between the expectation of the estimate and the true value of the parameter, right? So please note that the estimate is obtained as a function of the data, and the data are random variables. Therefore, the estimate is also a random variable and has its expectation. So if this doesn't sound very familiar to you, you may go back to the video on probability theory. So just to be on the safe side, this would be the expression for the expectation of this of the estimate, where since it is a function of a random variable, we apply the expectation, the expression for expectations of random variables, right? Where here we write the PDF of the data. So Note that the distribution of the data depends on the parameter that we want to estimate, right? So, for instance, in the MATLAB code of the previous slides, we were using the true value of 8 to generate the data vector, right? So this dependence will be emphasized by means of a subscript, but whenever it is clear, it will be omitted. And note as well that the bias will also be therefore a function of this of the parameter. This means that perhaps we have a low value of a low bias for some values of the parameter and a high bias for other values, right? This is something that we will typically observe. So back to the collection of estimates that we generated, it seems natural to think that a good estimator will provide estimates that do not differ much across realizations, right? So we generated all the realizations of the data vector using the same distribution and therefore the same value of the true parameters, and therefore we will not regard as reliable an estimator that returns 10 for one realization and 10,000 for another realization. So that is why another common metric is variance, which is just the variance of the estimate seen as a random variable, right? And this is of course by the definition of variance, and this is the integral form of the expectation. But variance measures the variability of the estimate around its own mean, right? However, it would be more natural to quantify the variability of the estimate around the true value of the parameter. And this is why another metric that we typically use is the so-called mean square error, and the integral form for the expectation is provided here. Note that all these three metrics depend on the true parameter theta, right? Some of them because they involve theta in their own definition, like the bias and the variance, but all of them because they involve the parameter in the PDF of these integrals over here. One of the main results in this context is the one that establishes that the MSE equals the variance plus the square of the bias. This is a very important result that arises everywhere in statistics and machine learning and so on. The proof is very simple. We just start by the definition of MSE and add and subtract the expectation of the estimate. Now, if we expand this square by considering these two terms separately, and then we obtain this expression. Now we can identify that this is precisely what we have defined as variance. This term inside this parenthesis is the bias, right? And since the bias is deterministic, right? Because we have already taken expectations in its definition, then here we will be taking the expectation of something that is deterministic, and therefore this expectation can be just removed. And regarding the third term, we have the expectation of the product of two terms. The second one is deterministic, and therefore it can come out of the expectation. So we have just something that multiplies the expectation of this term over here. But the expectation of this is just 0 because both terms cancel when taking expectations. Now that we know which performance metrics we want to use, we need a way to compute them. And that is not in principle straightforward because they involve expectations over the data, right? A method commonly used in this context is the so-called Monte Carlo method, named after the city of the famous casinos precisely for this reason. And the method is very simple. We draw our data realizations, and then, for instance, to compute the MSE, we just compute the square distance from the estimates evaluated at each of these realizations and the true value of the parameter, and then we just average. In the example of DC level estimation that we are considering, and this could be a possible MATLAB implementation, this function takes the DC level, the standard deviation of the noise, number of observations, this is capital R, and this would be a function which is the estimator. So as you can see, there's a for loop that iteratively generates one data realization and evaluates the estimator to obtain an estimate, right? And at the end of the loop, one just computes this square distance and averages it across the realizations. And this code could be invoked, for instance, with these lines here. And if we invoke it for all four estimators that we are considering, and also for multiple values of the true parameter, right, that we need to set to generate the data, then we obtain something like this, right? We observe that in general, this first estimator provides a pretty low MSE. The third one offers a very poor performance in this sense, right? However, we see that this fourth estimator sometimes works pretty well, right? We will elaborate further on this phenomenon. So this was the Monte Carlo method, which is extensively used in practice. However, it suffers from certain limitations. For example, it only provides the performance metrics for those values of the parameters that we specified. That makes it difficult to identify trends such as the MSC increases with sigma, or it doesn't depend on A, or things like that. So whenever possible, an analytical evaluation of these performance metrics must be carried out. And this is what we are going to outline next. So to this end, we will apply a conventional calculus of expectations to the DC level estimation example. Let us compute bias, variance, and MSE. Computing the bias essentially involves obtaining the expectations of the estimates. For the first estimator, we can just substitute its definition. Then we apply that the expectation of a linear combination equals the linear combination of the expectations. Here we just apply that the mean of the observations is A, and now we note that here we are just summing A n times, so the n, this n and this n cancel, and we obtain A, right? For the second estimator, we just substitute its definition and note that the mean of the data is A. Note that in both cases, the expectation of the estimate is exactly A, so they are unbiased, right? Because the bias is the expectation of the estimator minus the true parameter. For the second and for the third and fourth estimators, we can follow the same logic, and these are the values of the estimation of the expectation that we obtain. Regarding the variance, we need to be a little bit smarter here. So the variance for the first estimator here equals 1 over n squared times the variance of this sum. This is because of the properties of variance. And now here one can, of course, there are two ways of move forward. One way is to just apply the definition of variance. Then one gets a square, a summation inside the square, so it's a square summation times another summation. One can start multiplying the terms and applying the uncorrelation, that the variables are uncorrelated, and after several lines one arrives at the result. The other way, the short way, is just by realizing that these variables are uncorrelated along n, so the variance of the sum equals the sum of the variances, right? Again, this is explained in the video on probability theory that I mentioned earlier. Thus we are summing the variance n times, and the variance is sigma squared, so we will have n divided by n squared. We get 1 over n, and in the numerator we obtain sigma squared, the variance of the noise. For the second estimator, it is very simple. It's just sigma squared. For the third, we apply again the property. There's the same property as before. This 3 comes out of the variance with a square, and here there's a typo. There should be an x here, but the variance of x n minus 1 is sigma squared. And the fourth estimator is just the variance of a constant, and therefore it is 0. So observe that according to this metric, this estimator is the best, right? So that already indicates that the variance is on its own. It's not enough to characterize the performance of an estimator. To compute the MSE, we can similarly use the definition that involves expectations, and then we just use calculus of expectations as we have just done. And the other possibility is to use the result that we saw earlier, that the MSE equals the variance plus the square of the bias. So for the first two estimators, we see that they are unbiased, and therefore the MSE equals the variance, right? For the third estimator, there is both variance and bias, so both of them contribute to the total MSE. For the fourth estimator, we see that there's no variance, but there's quite a bit of bias, right? And we can plot them here, and we observe trends, and we can compare them for a wide range of A, something that is more difficult with the Monte Carlo method. What we can observe here is that none of these estimators is the best for all values of A, right? So for instance, for these values of A, the fourth estimator is the best. For these values of A, the first estimator is the best, right? So this is a very important message, and this idea shows up throughout statistics, right? As an exercise, you may compute what is this interval where the fourth estimator is better than the first one. Note that the second and the third ones are always worse than the first one, and therefore could be safely discarded. Now that we have developed the notion of what constitutes a good estimator, we need to come up with methods that allow us to design precisely good estimators. And a key step in this quest will be to come up with or decide which design criteria we would like to use. And this is impaired precisely by the fact that the performance metrics that we saw depend on the unknown parameters, and some estimators may be better than others for certain values of the parameters, but not for other values of the parameters. We will also be looking into the question of when a problem can be said to be difficult, or even more when we can claim that a problem has no solution. That's all for today. See you in the next lecture.